All right, so my goal here is to give you a worked example which is similar but not exactly the same as similar to 16.6 on page 26. So what I did is I made a totally different plot and I gave you some different knowns than I did in that workbook problem. So hopefully if you do this problem following along with the video, you could then try doing that other problem by yourself and see that'll give you an idea of how I might mix this up on exam day. So here's the information we're given. We're given this plot, which is made at time t equals 0. That's written right here, so I'm going to erase it from over here just to emphasize. So I need some room to work, basically. We're told the period, we're told the wave moves to the left, we're given this plot, and we're given the tension. We're going to try and figure out all these constants. If you don't know what those are, maybe watch the previous video again so you know what these are, but maybe I'll just say it real quick. Amplitude, wavelength, wave number. This is omega, not W. So that's angular frequency. V is wave speed. Mu, mass per unit length of the string. Phi is the phase angle. And lastly, after we get all this, we're going to try and write y of x of t. And if I remember, I actually have this plotted in Excel, and I'll maybe go to the Excel screen share at the end and show you what happens if we try different times or different phase angles, and you can see how that shifts the plot around. But let's say we're given this snapshot of a string, and for some reason it looks like this at this time, at least for the first 120 centimeters of the string. Notice something here. This is in centimeters, and this is in millimeters. So with a lot of these waves we've seen, the vertical scale is usually exaggerated so we can see the wave, but right, this is much smaller than that horizontal scale. All right, it's just blown up so we can see this. So let's try and figure out everything we can. If you want, you can pause the video now, and then I'll try and, or maybe I'll try and remind myself to stop right in between. What's the other marker I'm missing? There it is. All right, so I'll just try and do this in order. So I'm going to try and get the amplitude. If you want to try and do it yourself, pause. Here we go, amplitude. So that's going to be, I'm going to take lowest point and the highest point, and we see it goes 2.5 millimeters above, 2.5 millimeters below, or you could say the peak to peak distance is 5 millimeters. So the amplitude is half of that. All right, so the amplitude is half of the peak to peak distance. Got it. What's next? Wavelength. So before I try to get wavelength, I always want to look at what is listed on my axes. In this case, I'm given X on this axis. Sometimes we'll look at T on this axis. So in some wave problems, you use a fixed time and look at how the shape of the wave is versus X. On other situations, you pick a fixed point X and see how the wave is traveling through there as a function of time. So always look here. If we have X on this axis, you can get the wavelength from crest to crest. If T is on this axis, you can get the period from crest to crest. Got that? That's a sneaky thing I could do. I could mix this up on the test and put T here, and then you'd have to get the period from the graph, and the wavelength would have to be given. All right, let's get into it. So hopefully we can see this. Maybe we'll go from right here, crest. Well, how about we do this? This is a little bit past here. And then this one, also a little bit past here. My picture's not perfect, but the distance between these two crests should be the wavelength. See about what that is. So let's see, 20, 40, 60, about 80. Centimeters, because I'm on that axis. So sorry, I forgot to tell you to pause the video. Oops, whatever. So in this case, right, we're going from about 17 to approximately, or sorry, what is this? That's not 17, that's about 33 to about 113. So that's where I got the 80 centimeters, the distance crest to crest. And again, up and down, we use the vertical scale units of millimeters. Left and right, we're using the horizontal scale of units, centimeters. All right, wave number. If you want to pause the video, this is your chance. 1, 2, 3, go. All right, so K is 2 pi over the wavelength. I'm gonna get my calculator somewhere. Where did I put that thing? Oh my gosh, really? Oh, well, I've got it written down here somewhere. I got 7. Where did I put that calculator? Oh, it's right here. All right. So what I'm gonna do is I'm gonna use this in units of meters. So 2 pi divided by 0.8 is 7.854. We're reading everything off a graph. I think 2 sig figs is plenty here. We should try for 3, so maybe we should just round this right there. And this is meters to the -1. If you forget units on your test, you're going to lose points, okay? All right, so there's wave number. All right, omega. We're going to try and get omega. If you want to pause the video, this is your chance. 1, 2, 3, go. Omega is 2 pi over the period, which in this case, the period we were given in milliseconds, 55, which is 0.0555 seconds. If I did that right. Okay, so we're gonna go 2 pi divide by 55.5 e -3. I got 113.2. The units, 2 pi radians per second. Making sure that's what I had earlier. Yes, that matches. Okay, now what? V. What does V mean again? Wave speed. So there's lots of ways you could do this, I guess. You could use our old result, V equals F lambda. All right, so if you knew the frequency and the wavelength, that's good. But if we rewrite that, let's see, F is omega over 2 pi. And then we can multiply by the wavelength, which we know. We could do it that way. And that would be fine. But now what I would like to do is I would like you to notice that lambda, if we rearrange this, is 2 pi over k. Again, the other way would have been fine. Notice it's also omega over k. So either way would be good. We should probably use the one that's got less rounding error. So maybe that's this 80. So maybe I will do it the first way. So omega, let's see. Well, I guess you could also do it this way. Frequency is 1 over the period. And then wavelength we know. So this will have the least rounding error, right? So maybe we should do it this way. Lambda over the period. So lambda was 0.8 meters. And then I'm going to divide that by the period, which is 55.5 EE -3. And I get 14.41 meters per second. Let's see if that's what I got earlier. Yes, it is. All right. Next, we're trying to get wave speed. Wait, no, we already got wave speed. We're trying to get mu. What was mu again? Mass per unit length. So if you want to pause the video, go ahead. I'm going to do this in 1, 2, 3. Here we go. I know that V is equal to the square root of tension over mu. If you want to pause now that you have that hint, go ahead and figure it out. Here I go, 1, 2, 3. Go. When you rearrange this, let's see, you square both sides and switch the mu, you get mu is equal to tension over V squared. You might be wondering, why is he writing out the word for tension and instead of just using capital T? I don't want us to get mixed up with period, so sometimes I'll use the word period here instead of the double T or whatever. But so sometimes I just write out the words for clarity. That's all I'm doing, but you could use symbols. Typically, we use the double T for the period and the single T for the tension. So when you crank that out, what number do you get? Let's try it. Let's see, 3.33. And that's in newtons. And this is in meters per second. So our units should be all good. Divide by answer squared. I got 0.0. 0.01603 or something like that. Yeah, and that's in units of, because we use newtons, we've got kilograms per meter, which if we wanted to shift this to grams, 1, 2, 3, that's 16.03 grams per meter. So if you're using thread or string, maybe even some cables, it might make sense to use grams per meter. Whereas if you get to thicker cables or chains, maybe we would actually use kilograms per meter for units. So now that's all of this stuff except for the phase angle. We've done this. So in order to figure out the phase angle, I'm going to need a little bit of room. I'm going to erase all of this now. So if you want to, okay, whatever, you can always come back and look at it. So we're going to try and figure out the phase angle. While I'm erasing, you can try and imagine how to do it. Think. I'll catch up. Right? Phase angle. Here we go. 3, 2, 1. So I can tell usually, well, so I'm going to actually write our wave equation first, and then we're going to be missing the phase angle, so we'll fill that in. I know that y of x and t is equal to amplitude sine of kx plus or minus omega t. And then what did I use? Plus a phase angle or minus a phase angle? Let me see what I used here. Plus a phase angle. Right? It doesn't really matter. This second, yeah, whatever. I'm going to shut up now. Let's get to work. Which sign do I use here? Plus or minus? Here we go. 1, 2, 3. To the left means we should use the plus sign. That's where I got this plus sign. Okay, moving to the left. Make that look a little neater. Now, we know that this particular snapshot was made at time t equals 0. So this is going to be 0. And now what I could do is I'm trying to learn about the phase angle. I could pick one particular value of x. A convenient one might be 0. And notice that says y of 0 at time equals 0 is a sine phi. Said another way, -2 is a sine phi, because that is y at x equals 0, and this entire plot was made at time equals 0. So this number here is y 0, 0. Y at x equals 0, t equals 0. I know the amplitude already. I erased it, but I think it was 2.5. So take a look. Let's just write this out. Y 0, 0 is equal to amplitude sine of phi, because all the other parts inside this wave equation are going to, this solution to the wave equation are going to drop out. So now I know the amplitude and I know this. Let's plug in that info. Let's solve for this. Phi should be sine inverse of this over that. Which in this case is sine inverse of -2 millimeters over positive 2.5 millimeters. And amplitude is always positive. Amplitude is peak to peak divided by 2, which was 2.5 millimeters. So notice we'll have a negative number here. What do I get for that? Sine inverse -2 divide by 2.5. And my calculator is in degrees mode. I get, let's not spend all day on this. Let's just say it's -53.1 degrees. However, anytime you take an inverse trig function, you have to think about the other solution. So I'm just going to kind of draw a quick visual here. -53.1 is maybe right here. Okay, so notice the vertical component is negative. The other angle, which gives me that, is right here. The trick to getting this is you take 180 degrees minus your other result. So 180 degrees minus -53.1 gives me, what is that? 180 plus 53.1, which is that 230, 231 or so? I'm pretty tired. It's been a long day. Let's just make sure I didn't screw that up. Yeah, that looks about 233. Oh, it was a 0.1. My bad. There we go. So it's one of these two options. All right. How can we tell which one it is? We should not blindly assume it's -53.1. All right. So in this case, what do we know? This wave moves to the left. How does that help us? Let's imagine this wave moving to the left. A millisecond later, this portion of the string should be higher up. If this wave is translating this way, a minute later, this point would be at the origin. So we expect that the velocity in the y direction of the element of the string at x equals 0 at time equals 0 should be greater than 0. What? All right, I'm running out of room here. Well, let's take a look. If you take a derivative of this function, what's going to happen? The phase angle won't do anything. When we take a derivative, we'll get a positive omega popping out. Obviously, if it was a left moving wave, we get a negative. That would be a little bit trickier. So for a left moving wave, watch your minus sign. Or sorry, for a right moving wave, you would have a negative here, and that would be a little bit trickier. Basically, watch your signs like a hawk. Whenever you're getting phase angles, please take an extra second to watch your signs. All right, so when oh, and this would be a cosine function, wouldn't it? Taking the derivative of sine gives you cosine. So now if we set this to 0 and this to 0, that would set this to 0 and this to 0, right? And so we get Vy 0, 0 is omega A cosine of phi. Think, we want that quantity to be positive. Omega is a positive quantity. It relates to the period, which is a positive number. It's a time. A is the amplitude. That's a positive number. We need a result such that cosine of phi is positive. Well, look at these two phase angles. This one has a positive value for cosine, a positive x value on the unit circle. This one has a negative value. So in this case, negative 53.1 is correct. 233.1 is wrong. And so if you wanted to write this wave equation, we could now stick all that information in. And maybe I'll actually do that, but I'm running out of room, so I'm going to have to erase this. So what did we say? We said the phase angle is negative 53.1. Okay. Not 233. So now I can write y of x and t is equal to, we have to be careful now. If we're going to plug in the numbers for amplitude and all this nonsense, we should include the units. So when you have an equation with known parameters with units and variables, you should put the units on the known parameters because that will affect somebody that wants to plug in information. Let me show you what I mean. We could just write this as a sine kx plus omega t plus phi and have the numbers all written somewhere else. But if you want to write this with the numbers plugged in, it's basically being considered to include the units here. So what did we say? 2.50 millimeters sine of, what was K? K was 7.85 meters to the -1. I'm being a little sloppy with sig figs here. We should probably include 4 if we want our answers to be correct to 3. But since I was getting this from a graph, I'm going to include 3 and assume our answer is correct to 2. So then we have x. Then we do plus because we're moving to the left. And then, oops. What was omega? Wasn't it 113 or something? Go out of here. P was 53.1 negative. Okay. Times T. Keep an extra digit if the first is 1. And then minus 53.1 degrees. We could convert that to radians really quick. So a lot of times we would just write 53.1 degrees in here, and then you'd have to know you're going to have to change everything in your calculator to radians to make this work. But let's just write it in radians this time. 53.1 times what? Pi div 180 minus 1, 2. And then maybe I'll put parentheses around that. All right, so there's our wave equation, and I hope that that's the shape of this wave as a function of time. And I said I would show you the Excel sheet in case you wanted to see this, so let's do that really quick. I think I need to do a screen share. All right. All right, so this is the data sheet I made up to make this work. And so my amplitude was here. There's my phase angle in degrees. There it is in radians. Here's my wavelength, okay, et cetera. And you can see this all the way across. And then the fun part is what happens if I change the phase angle or the time? Let's start by just changing the time. If I say this is 1 second, we see it's moving a little bit, or if it's 0.1, right? All right, so we could see that the wave is moving around. If you use different time values, the shape of the string looks different because this sine wave will be shifting around. So let's go back to 0. And what if I change the phase angle to 0? There we get a normal sine function. If I go 1, 2, 5, you can see that a positive phase angle is shifting the plot to the left, right? And if we go all the way up to positive 90, it shifts it into a cosine function. Now let's go negative. We start with 0, we'll try negative 10. It's shifting the plot to the right. A negative phase angle is shifting it to the right, in this case, based on the way the equation was written, because we said plus v in the equation. So go up to plus 20. Whoops, sorry, negative 20. Let's go up to negative 30. And then finally to, what was it, negative 53.1. If you go to negative 90, think, you get a negative cosine. All right, so I think that's enough. Let's stop the share. And let's end this.